Hello everyone, I am Dr. Devapabyam, Assistant Professor of Physics, Government College for Women, Kolar. Welcome to my video lecture on Work and Energy, session number 15. This topic includes work and energy, definition of work and its unit joule, different types of works like positive, negative and zero works, work done by constant force, work done by variable force, work done by multiple forces, statement and proof of work energy theorem. Learning objectives to make the students understand definition of work, definition of unit of work joule, distinguish among different types of work, expression for work done by a constant force, expression for work done by multiple forces, expression for work done by variable force, statement and proof of work energy theorem. Learning outcomes. Students are able to define work and joule, classify work based on the sign of the work, derive expression for work done by constant force and variable force and multiple forces. State and prove work energy theorem. Prerequisites. Concept of work and joule, concept of force, concept of displacement, concept of energy, relation between work, force and displacement, relation between force and energy. Work. Work is defined like this: the product of the force exerted on the object and the displacement of the object along the direction of the force is called work. Suppose force F acting at an angle theta with x direction makes the displacement of the block through displacement S. The horizontal component of force is F cos theta, vertical component of force is F sin theta. Therefore, work is equal to dot product of vector F and vector S. Now this is equal to vector F is, you have to consider horizontal component of force F cos theta, magnitude of vector S is S. Now this is equal to Fs cos theta. SI unit of work is joule. 1 joule is defined like this: work is said to be 1 joule when a force of 1 Newton moves a body through a distance of 1 meter along the direction of application of force. Positive work, when the component of the force is in the same direction as the displacement. So like this, theta is always less than 90 degree. Work is positive. Theta is less than 90 degree. Then cos theta is always positive. Therefore, work done is positive. Example, a freely falling body under gravity. Gravitational force is always acting towards the center of the earth. If a falling body is also towards the center of the earth, then theta is always 0 degree, cos 0 degree is 1. Therefore, work done is positive. Negative work. When the component of the force is opposite to the direction of displacement, then theta is greater than 90 degree. W is equal to negative. Why? Because a body is lifted upwards, work done by gravity is negative. When a body is lifting upwards, gravitational force is acting downwards. Theta is 180 degree. Therefore, cos 180 degree is negative and then work done is negative. This is a case where theta is greater than 90 degree. Work done by force is negative. Zero work. If the force is at right angles to the displacement, theta is 90 degree. W is equal to Fs cos 90 degree. Cos 90 degree is always 0. Therefore, work done is 0. Example, a laborer carrying some luggage on his head and walking along horizontal road. Here what happens is, the head is always supporting and weight is always acting downwards. Then theta is 90 degree. Work done is 0. Work done by multiple forces. When several forces acts on a body, then the net work done on the object is the sum of the work done by individual forces. Now take work done by force 1 is W1, work done by force 2 is W2, work done by force 3 is W3 and so on. Work done by nth force is Wn. Then total work done is W1 plus W2 plus W3 plus so on plus Wn. then net work done W is equal to vector F1 dot vector S1 dot plus vector F2 dot vector S2 plus vector F3 dot vector S3 plus so on plus vector Fn dot Sn vector. Now we can also write it as summation W is equal to sigma I is equal to 1 Wi. Now this is also equal to sigma I is equal to 1 to n Fi vector dot Si vector. Work done by a constant force. A constant force vector F acts on a body at angle theta. Work done W is equal to Fs cos theta. Velocity of particle changes by force. Now you know the equation of motion V square is equal to V naught square plus 2AXS. Multiplying throughout by m and divide throughout by 2. We get half mv square is equal to half mv naught square plus max s. Now shift this half mv naught square to left hand side. Half mv square minus half mv naught square is equal to max s. Now left hand side terms is the difference in kinetic energy, that is final kinetic energy minus initial kinetic energy. This is equal to max is force into displacement is work done. So therefore work done is equal to change in kinetic energy. The net work done by the force is equal to the change in kinetic energy of the body. This consequence is called work energy theorem. Work energy theorem statement. The net work done by the force on a body is equal to the change in its kinetic energy. If the applied force increases the velocity from V0 to V, work done is W is equal to integral of F dot ds. Now, you can also change force as F is equal to ma. Now, this is equal to m into acceleration is rate of change of velocity. So, dv by dt. Now, this is equal to m. I will change the variable in the denominator. Multiply by ds, divide by ds. Now m into dv by ds into ds by dt. This is equal to ds by dt is velocity, rate of change of displacement. So therefore m as it is, ds by dt is v and retain dv by ds. Now f dot ds can be replaced by mv into dv by ds into ds. ds cancel with each other. We get w is equal to mv dv. Now integrate this term. W is equal to integral of mv is half mv square. Substitute the limits. Initial velocity v0 to final velocity v. Now this is equal to W is equal to half mv square minus half mv0 square. This is change in kinetic energy. Therefore work done is equal to final kinetic energy minus initial kinetic energy, which is equal to change in kinetic energy. Work done by a variable force. A force whose magnitude and direction change continuously is known as a variable force. Suppose force F is taken along y direction and displacement is taken along x direction. Consider a variable force acting on an object that moves along x-axis. It is assumed that the force remains constant over small displacement delta S1, delta S2, delta S3 and so on. Now this can be graphically represented like this. Now the object is displacing in this direction, which is along a curve from capital A to capital B. Now we can consider this entire region and divide the area under this curve into small rectangular elements. Now we assume that force is constant in the very small region. So this is delta S1, this is delta S2, delta S3, delta S4 and so on. The path length AB is divided into a large number of very small displacements. Total work done W is equal to delta W1 plus delta W2 plus delta W3 plus and so on plus delta Wn. Now W is equal to this delta W1 can be written as F1 cos theta 1 delta S1 plus delta W2 can be written as F2 cos theta 2 delta S2 plus delta W3 can be written as F3 cos theta 3 delta S3 plus so on. Delta Wn can be written as Fn cos theta n into delta Sn. Now total work done W is equal to sigma I is equal to 1 to n Fi cos theta I delta I psi. This can also be written as Fs cos theta, which is area of AABB, area under the curve AB, which is equal to AABB. Work done by the forces, work done by a variable force, which is equal to area under the curve. Summary. So far I have defined work and its unit of work joule, studied positive, negative and zero works, derived expression for work done by constant force, derived expression for work done by variable force, derived an expression for work done by multiple forces. Statement and proof of work energy theorem was studied. Thank you.